Let's do problem number 19. One end of a uniform 4-meter long rod of a weight Fg is supported by a cable. The other end rests against a wall where it is held by friction, as shown in the figure. The coefficient of static friction between the wall and the rod is μs equals 0.5. Determine the minimum distance x from point A at which an additional object, also at the same weight Fg, can be hung without causing the rod to slip at point A. I drew the diagram here. I need to find this distance x at which you can keep hanging this ball, and it's a certain distance is going to give way and the plank is going to fall down. So you just need finding that little distance here. And so given by the problem, this ball exerts a force Fg down, and so does the plank, but at its center of mass, which is a very important detail, that it exerts a force Fg down, but at the center of mass. And the problem also tells you that the only thing keeping this board up is this force of friction, which you can just call μn. I'm gonna label the tension right here. It is at a 37-degree angle. That means this tension is gonna have its x and y components. I'm gonna write the x and y components of the tension here to make it easier to view. The x component of the tension will be t cosine 37, and the y component of your tension is gonna be t sine 37. Since this plank is against the wall will exert a normal force back at the plank. So to start solving this problem, you're gonna want to sum up your forces in the x and y direction. So real quick, top is positive, and to the right is positive in the x direction. Let's sum up our forces in the x direction so we can find normal force, and then we'll know what our friction is. So when you sum up your forces in the x direction, relatively simple. Normal force minus that x component of the tension, because normal force is that way, and your x component of the tension, since the string is that way, is going to be that way. So normal force minus the x component of tension will give you ma, but since it's not moving at all, this is static equilibrium, set it equal to 0. And so the normal force is equal to t cosine 37. And to make things simpler, I'm going to evaluate cosine 37, turn it into a decimal. This will make solving the problem much easier. So normal force is roughly 0.8 times the tension. Next, sum up your forces in the y direction. So in general, when sum your forces in the y direction, you're going to have the y component of the tension plus that frictional force minus these two Fg's. So let's do that. T sine 37 plus the frictional force mu n minus 2Fg equals ma, or 0 because static equilibrium. None of this is moving. And also, once again, I will evaluate sine 37, make it easier to view and solve. So that'll be 0.602t plus mu and our normal force, 0.799t minus 2Fg equals 0. I'm going to start solving for tension. So negative 2Fg equals negative 0.602t minus 0.399t. Add those two together, divide. Tension is roughly 2 times that of the weight of the ball or the plank. You may be thinking now that this is not getting you anywhere. So since we are trying to solve for this distance x, we need to think of a formula that incorporates like a distance from the center of mass or that kind of thing. And that's going to be torque, which is Rf sine theta. And the R is the key. And so the key to solving this problem will be summing up your torques and solving for that R. But another really crucial point is that you sum up your torques right here. This makes it such that you don't have to deal with this frictional force or normal force, since if you make this your axis of rotation, you don't have to worry about any of that, which makes solving this problem a lot easier. So let's use that as our axis or point of rotation. So if we sum up our torques right there, let's kind of visualize that this y component of tension will be pulling the plank in this manner. And so we're gonna call, this motion or counterclockwise positive. So this y component of tension will give you positive torque, while these two weights will give you negative torque. So the torque due to tension minus the torque of the ball minus the torque of the plank will give you I alpha, or 0, because it's at static equilibrium. And next you're gonna want to start plugging stuff in for the torque due to tension. Your R is just going to be the entire length of the board, which is 4 meters as given in the problem, since the y component of the torque is applied right here, and its distance to the axis of rotation is 4 meters. So you'll write 4 meters times the y component of tension, which is t sine 37. You're going to subtract the torque due to the ball, and its radius, its r value is going to be just x, which is what you're solving for. And that x is its distance from the axis of rotation multiplied by its force, which is just Fg. And you don't have to worry about sine theta in any of these because they're all being applied at 90-degree angles. Once you have the torque due to the ball, you can do, wow, did I really write torque? I meant plank. Minus the torque due to the plank, which will just be, since the torque due to the plank, its weight is being applied at the center of mass, its distance to the axis of rotation will be 2 meters, because the center of mass is right down the middle of the plank. So you'll write 2 meters times Fg equals 0. And now it's a piece of cake. You just start solving things and whatnot. You can solve for x here. You'll get, once you multiply 4 times sine 37, you'll get 4.815 Fg. And then it's just minus xFg minus 2Fg equals 0. You may say, oh, there's 2 unknowns, but just divide everything by Fg. Don't gotta worry about that. You get 4.815 minus x minus 2 equals 0. Solve for x and you get 2.81 meters. This is how you solve problem number 19 of chapter 12.